to show that the volume of three-dimensional space contains some certain amount of matter, and this space has a length, a width, and a height, and this would be three-dimensional. And time, on the other hand, is just one-dimensional. And if you add time and space together, then you get 4 dimensions with a D, 4D, but for some reason I didn't write a D. And so you can represent this by saying that space equals S. S represents space and T represents time. So 1 dimension of time and 3 dimensions of space equals 4 dimensions. Gives you a 4-dimensional surface, so to speak. And on the axis of time we have energy, and on the axis of space we have matter. And so you can say that these are related by mass equaling the square root of energy squared plus matter squared. It's proportional. I don't know if it equals, but it's proportional. And so a spot on this surface can be represented by a 90-degree angle, with one side being of energy and the other side being of matter. And so now let's delete this. And so now that we have defined that, let's go ahead and draw a square and put mass inside of it, and then label the sides as being of length A. And then we can say that the density is equal to the mass contained within the volume, which is equal to mass density of matter, which equals mass divided by A cubed, with A being the length of the sides. And then for energy, we can draw a cube of space again, and since energy doesn't have mass, we have to say something along the lines of, let's just say the volume still equals A cubed, just like it does for matter, but we don't have mass now, so we have to use something like energy equals, Planck's constant times the frequency, which can be written as Planck's constant times the speed of light squared divided by the wavelength. And the wavelength is, I guess that's it for that part, so yeah, let's just do that, then never mind. I was going to say that, so let's just say that, A is proportional to the wavelength, because it's contained within this box. And since E equals 1 over, or is proportional to 1 over the wavelength, it's also proportional to 1 over the sides of the box, or 1 over A. So that means that E equals N over A explicitly. And it's just some constant time over a, and then we have, so if we multiply that by the volume, then we can get well, let's multiply this side of the equation, keep it consistent. So we have volume times energy equals N over A times volume. That would equal the energy density of, yeah, or we can say rho sub E. So let's say rho sub N for mass and rho sub E for energy. And so if we go ahead and multiply that out, we'll see that density of energy is equal to N over A to the fourth power. So that's kind of like mass is contained within the 3 dimensions of space, and energy is contained within the 4 dimensions of space-time. And so let's continue with this right here. So let's draw an energy well. And so an energy well is like a box, and it has a length along the x-axis, just label it x, and it has a length of from here to here of L. That's the inside of the box, and then it has a height of potential energy of V0, and a total, it's along the potential energy axis. And so let's see, so what am I doing? I think that we can just say E equals N over A to the fourth power, as we already proved. That's time and space dimensions. And so you can think of this energy well, if it gets smaller and smaller and smaller along the x-axis, then it can become just a straight line here. So its energy potential is just a line, and x remains on the x-axis, and then so L would be 0 because it has no length now. And so if we plug that into the equation for energy, we would see that energy goes to infinity because the length goes to 0. And so an energy well of length 0 has infinite energy. And that's kind of like, E equals infinity, so it's like a black hole. You can think, point of singularity, matter falls into a black hole, gets converted to energy, and keeps increasing towards infinity. And so the black hole's going to spiral inwards as the energy increases. And you can think of the matter lying around the black hole as being on the x-axis in space, and the energy along the potential energy axis in time. So we got the fourth dimension going through the center and 3 dimensions surrounding it. And that's basically what a black hole looks like. Now, people say that if you fall into a black hole, you can never escape it. But I think the Schrodinger wave equation can be used to prove that things inside of a black hole can still escape from inside of it. And I believe that contrary to current science, I believe that everything around us exists as matter because of the energy inside of our black hole in the Milky Way. There's a black hole at the center of our Milky Way, and that's what's giving rise to all the matter that surrounds it. So if you take the Schrodinger wave equation and then you solve for it, you can find a very interesting result. So basically at this point we have that the energy times the Schrodinger wave equation is equal to a weird thing. I don't know what it is. It's kind of like the momentum, I guess. It's kind of like how much energy is contained within I don't know what it is. Anyway, it's the Schrodinger wave equation. So it equals this. It's like the rate of change. It's like the acceleration along the x-axis of the matter wave. So let k squared equal 2m over h bar, and then the potential minus the energy. Then you can say that the phi, which is the Schrodinger wave, is equal to, or the solution would be a to the e kx plus e to the, or b times e to the negative kx. And I can prove that that's the solution because Dr. Physics A told me so. But if you, so if this equals, if we take the derivative of phi, we would get that, bring down the k. Just go ahead and bring it down. I think I've noticed something. I'll just continue here. And then that, and then plus, and then bring down the k. Well, not plus, minus, then bring down the k, b, e to the negative kx. Alright, now let's look at this. Why do I have a t? I think that should be x. Pretty sure that should be x. Alright, let's take the second derivative. So do the same thing again. You're going to get, bringing down the k again, you're going to get k squared this time. A e kx plus, imagine that, plus k squared b e to the negative kx. And then we can, alright, and then that equals k squared times this whole thing here, e and plus bk negative. Alright, we get this, but this is the same as this, which is phi, so I can replace all this by phi, so this equals k squared times phi. Alright, so I proved that that's the solution for the Schrodinger wave equation for a particle in a box, which we're going to apply to a black hole. Alright, so if we apply the Schrodinger wave equation for a particle in a box to that of a black hole, then you can say that, well, let's look at the solution again. We have a times e to the k, where's my, kx plus Now, what does this first term do? According to Professor Physics A, and he's right, it would do this, which goes off to infinity, so that's not a valid solution for what we're looking at. We need something that goes to zero as it goes along the x-axis. You know, the further it gets away, it should decrease, not increase in energy. So this would be normal. This would make sense. So we're going to use this one. The other one doesn't make sense. How can something increase in energy the further away it gets from the source? So if we let psi equal b e to the negative kx, then we have an exponential decline from our box. So if you have energy trapped within this box, like a black hole, then according to the wave equation, we can actually have things appearing outside of the box. Even though it didn't go over it, it goes through it. So what's going on inside the box can actually create matter outside of it. And this is kind of how a black hole works. If we decrease the black hole, then the energy increases, and we create matter closer to the event horizon. And the more energy the black hole takes on, the closer the matter will be created to the event horizon. And when the energy inside the black hole becomes infinite, then nothing can exist outside of the black hole. So it's kind of like the life of a black hole that's gaining energy, where everything that surrounds it falls into it, and new matter that's created from it will become closer and closer to the event horizon as the black hole increases in energy. So you can escape from a black hole because of the because of the Schrodinger wave equation. We exist. Every particle created in our solar system was created because of what's going on inside of the black hole at the center of our Milky Way. We exist because of what's going on inside of the black hole. You and me and everyone. We escape all the time from a black hole. That's why we're here. Am I done drawing yet? I don't know why I'm drawing this. What am I doing? Oh, there I am. I'm falling into the black hole as it gains energy, or it doesn't even have to gain energy. You have gravity pulling into you. You have these forces. You have the force of gravity, and you also have this wave equation. So you have these two things. Wave equations acting upon new matter, and gravity acting upon old matter. Wave equation acting upon old matter, and I don't know, it's all messed up.